Hi, see you again. The next video. Okay. So we will continue our lesson in Q theories. So now we will discuss subtopic 1.2, various Q models. Okay, Q models. MM1, MMM, MD1, MM Infinity, etc. Okay, what are those MMMMM? Okay, first let's see MM1 Infinity. So what is this? You still remember pattern? This one. The format. Okay, format. This one. Okay. The first M is arrival process. The first M represent memory less property M. For example, Poisson arrival process. What is this? What is the meaning of this? Poisson arrival process. Poisson normally is the pattern. Pattern. You can we will get somebody to describe about this later. The customer arrival rate is represented by this. What is this? This is lambda symbol. Service distribution, the second M, the first one is arrival process, M, memory, or Poisson. The second one is service distribution. The second M represent memory less property, exponential service time. The service rate is represented by, what is this? This is micron. Micron. And the meaning of exponential distribution is given by, the mean average. The mean of exponential distribution is given by 1 over micron. 1, this one, present number of servers. So you still remember this one? This one. S. This number of this one. Number of servers, S. Okay. So this one is number of servers. Okay, 1 is without S lah. Without S, sorry. Infinity represent that the queue length can be infinite. Of course, we know that in the world this cannot be true. So what is this infinity? Infinity represent the S. Sorry, this one, capacity. That infinity represent capacity. You still remember? K system's capacity, maximum number of the customer in the system, including the one being served. Typically, we omit this when it's infinity. So this is infinity. So now this is MM1 Infinity. So infinity represent that the queue length can be infinite. Finite means infinity. Of course, we know that in the real world this cannot be true. So this is the figure to represent this. So arrival rate lambda. Okay, and then we have service rate micron. Okay. Second one, we have MMC10. So what is MMC10? M, the first M is refer to arrival process. M represent memory. Okay. The second M is service distribution M. M also represent memory less. Okay. C, the third one is C, represent number of servers. Okay. So C represent number of servers. In our case, 2. This one, this case 2. And 10 represent the capacity. The K represent the maximum length of the queue, 10. Okay. So 10 is K, right? A, B, S, K. Okay. So 10 is K. The capacity is 10. Okay. Other examples of queuing system could be like MG1, MD1, etc. So other example could be MG1, MG1, MD1, MD1, etc. So in this case, this one, the C become 2. So where is the 2? So now we have one server and two server. So this is in this case MMC 10. C represent number of servers. In this case, we have two, 1 and 2. Okay, MM1. Out of all the different types of queuing system, MM1 is the simplest queuing model. We have arrival memory, and the second M is what? Service distribution. M also, and only one server, MM1. This is the simplest type of queuing system, queuing model. Okay, the simplest. We can model the output link of a router as MM1 queue, which is actually what we will do later in the example. So normally we will model using the simplest model, simplest example, MM1. Okay, so M, arriving distribution. Okay, arrival process, service distribution, and number of servers, M1. Okay, so this is the example of the model. So you have one server, one arriving customer, one. So here you only have also one. Okay. Okay, next we will discuss about properties of a queuing system. Properties of a queuing system. At this point, we know that the queuing system can have customer arrival rate, lambda, which tells us how fast the customer are coming in, and service rate, micron, which is the average time taken to serve each customer. A good queuing system has a property that service rate micron is greater than the customer arrival. Okay, so micron is greater than lambda. This is a good queuing system. And the ratio lambda over micron is represented by, what is this? This is rho, or you can say, I don't mind if you call this as p, but I think this is rho. This is Greek number, Greek alphabet. So this is p or rho. So this is, let's say p lah, p, because it look like p. Okay, P is lambda over micron, or the customer arrival rate over service rate. Should be less than 1. Okay. Okay, next is properties of a queuing system. Typically, we are interested in getting the value for below parameters for a given queuing system. So parameters, what parameters? W, Q, TS, TW, TQ. These are the parameters. W is numbers of customers waiting in queue. Q, total number of customers in the system waiting and being served. TS denote as the service time, 1 over micron. TW, waiting time in queue. And TQ denote the total turnaround time, waiting time plus service time, which means TQ, this is the equation. TQ equal to TW plus TS. So what is TQ? TQ is the total turnaround time. Total turnaround time equal to TW, waiting in queue, plus service time. Okay lah. So total turnaround is waiting plus and service time. So waiting plus service time. So this is called total turnaround. Okay. So this is the figure shows the properties of a queuing system. So we have arrival rate, waiting line queue here, 1, 2, 3, 4, 5, for example. So W equal to number of customers waiting time. TS, service time at the server. So service rate is micron. So TQ is total time from arrival till finish, waiting plus being served. So this is a TQ. Okay, so basic queuing relationship. Little's law gives us below two relationship between the parameters for any steady state queuing system. Q equal to lambda TQ. Question 1. Question 1. W equal to lambda TW. So this is question 2. When first read about it, we should obviously call obvious law, and it was pretty intuitive. So this is, say that this is very straightforward. So TQ means mean time in the system. TQ, time in the system, the average time in the system. Okay, steady state flow rate for coming and for out of the system. So basic queuing relationship. In case it's not really clear to you, think about the basic relationship between distance, speed and time. So distance, speed and time, which we are very familiar. So basically distance is the speed multiplied by time. Ini kita dah biasa. So distance, jarak ialah laju darab dengan masa. The distance covered is a product of the speed of the object moving and time taken. Now assume that the arrival rate, lambda, is the speed and the waiting time is time spent. This will give us the length. We are not going to prove Little's law, but if you have an interest, the proof is widely available in the textbook. Okay, so next. Relationship between total turnaround, queuing and service time. Okay, total turnaround, what is this? Queuing, what is this? And service time. In a queuing system, a customer's time is either spent waiting for service or getting served. Okay, so in the queuing system, system queue, the time taken by customer is either spent waiting, I think TW, right, or getting or being served. getting service or being served lah. Yes. Thus we get this relationship. TQ turn around. Turn around ni TQ. TQ equal to TW plus TS. So it is very obvious lah. Total turnaround is the time waiting plus being served. Okay, clear? Multiplying the above equation by the arrival rate and applying latest formula we get. So we multiply all this equation by arrival rate lambda. So everybody is being multiplied by lambda. So this one, this one, this one. From the earlier equation, 1 and 2. So that Q equal to lambda TQ and W to lambda TW. So we get Q equal to W plus lambda TS, where TS equal to 1 over micron and P equal to lambda over micron. So therefore, Q equal to W plus lambda over micron equal to W plus P. This you need to rewrite again. Rewrite all this equation. Otherwise, you will be burning. So you'll be mixed up. So this is simple equation, simple derivation only. Okay, so you need to rewrite this again so that you can understand a bit more. Okay, so analysis of MN queuing system. It's time for us to derive some equations. And MM1 queuing system is a single queue, single server queuing system in which arrivals are Poisson and service time is exponential. The notation MM1 describes the queue in the system as having a Markovian arrival, Poisson and Markovian exponential service discipline with only one server. Okay. So I think we will end here. So we will continue later in later video about probability of arrival and departure. So we will discuss this in the next video. So that's all. If you have any question, you can always ask me, or you can always comment. I will attend to the comment. Okay, that's all. That's all for now. We will continue again later. Okay, bye. Assalamualaikum.